Thompson's atomic model, also called plum pudding model. According to this model, atom is made of positively charged matrix and negatively charged particles are embedded. So this looks like plum pudding, or you can say watermelon. So in plum pudding or watermelon, there is a spongy matrix and seeds or plum. Seeds in the case of watermelon and plum, nothing but fruits. Fruits are embedded in spongy matrix, isn't it? So similarly, in the case of plum pudding model, Thomson assumed that there is positively charged matrix. Within that, negatively charged particles are embedded. So based on this picture, he could able to explain first one, electrical neutrality. Electrical neutrality means net positive charge is equal to net negative charge. Thereby, total charge of the system is 0. Many experiments revealed that atoms are electrically neutral. So, this model supported electrical neutrality. Second, the model also explained stability. Stability means there is no question of decay of this atom according to atomic model, isn't it? There is no reason that this atom can disappear or decay. So the atomic model also explained stability. Now what are the demerits of this atomic model means? Demerits or failures. First one, the atomic model could not explain origin of spectral lines. Origin of spectral lines. Origin of spectral lines means in the case of bulb, CFL or LED, due to electrical energy we have observed emission of radiation. So modern atomic models could explain emission of radiation from the atoms. So let us see origin of spectral lines and spectral lines in the next topic. Okay. For time being, the atomic model, Thomson's atomic model, could not explain origin of spectral lines. And second, this atomic model could not explain large angle scattering. Large angle scattering. Large angle scattering means if this is the nucleus, suppose positively charged, and if a positively charged particle is projected towards the nucleus, just like alpha particle, because of positive repulsion, the alpha particle experiences larger force. So direction of motion of the alpha particle changes. So this is the initial direction of motion. This is the angle through which alpha particle is scattered. Observe, this angle is greater than 90 degree. So greater than 90 degree means it is large angle. So this type of scattering cannot be explained using plum pudding model. In the next model, Ruthefords atomic model, we can explain this. So for 2 marks, merits of Thomson's atomic model. Atomic model could explain electrical neutrality and stability. For 2 more marks, disadvantages or demerits or failures. The atomic model could not explain origin of spectral lines and large angle scattering. Rutherford's alpha scattering experiment. This experiment is also called Geiger-Marsden experiment. Rutherford suggested the experiment and Geiger-Marston performed this experiment. So in this experiment, bismuth 124, it is an isotope of bismuth, radioactive isotope, is used to get alpha particles, and this bismuth 124 emits alpha particles of energy 5.5 MeV. M is mega 10 power 6, electron volt is unit of energy, isn't it? So 5.5. Most of the alpha particles emitted from bismuth is of this energy, 5.5 mega electron volt. And then a thin gold foil was used. So thickness of that gold foil was about 2.1 10 power minus 7 meter. So you can say 21 10 power minus 8 meter or 210 nanometer. Okay. So it's a very thin gold foil. Now, if this is a source of alpha particles, bismuth 124, since it is radioactive, it also emits gamma radiation. Okay. So usually radioactive elements are taken in lead cases with small gap, and through this gap alpha particles are emitted. To get fine beam of alpha particles, lead blocks are used. If lead blocks are used like this, and if gap between the lead blocks is very small, then only those alpha particles which can travel through the gap emerge. So as a result, a collimated beam, fine beam or collimated beam. Collimated beam of alpha particles is obtained. So why these lead blocks are used means to get this beam, collimated beam, because from this source alpha particles are emitted in all directions. So those alpha particles which are emitted in the backward direction are blocked by this lead, and remaining are blocked by this. Thereby only those alpha particles which can pass through the gap will emerge. Then a gold foil is placed. So this is the gold foil. To detect alpha particles, zinc sulfide is used. Zinc sulfide is a fluorescent material. Zinc sulfide is a fluorescent material. What is fluorescent and fluorescence means? If this is glass plate, and on the glass plate if there is a coating of fluorescent material, when radiation falls on the fluorescent material, there is emission of radiation. So immediate emission of radiation due to the incident radiation of suitable energy or frequency is called fluorescence. Delayed emission is called phosphorescence. You might have seen phosphorescent stickers, also called radium stickers, isn't it? Those stickers are pasted in kids' room in the ceiling. As long as radiation is falling, light is falling on the sticker, it absorbs energy, and after some time it starts emitting radiation. So there is delay of emission of radiation. So such materials are called phosphorescent material, and the phenomenon is called phosphorescence. Fluorescence means the one which is used in reflectors. So as soon as the light falls on the sticker, it emits light. So instead of using light source, stickers are used. So that is more economical and more durable. Okay. So here, if alpha particle falls on the zinc sulfide, suppose this is the glass plate coated with zinc sulfide. If an alpha particle hits the zinc sulfide, momentarily there is emission of radiation. There is a flash of light, also called scintillation, sparks like. Okay, so because of this we can understand that there is alpha particle hitting the zinc sulfide screen. If number of scintillations are observed, number of sparks are observed, then we can conclude that more number of alpha particles are falling on the screen. Okay, so such detectors are used, and to observe scintillation, microscope is also used. If this is suitable microscope, as soon as light falls on the phosphorescent material, scintillations are produced. To observe carefully, microscope is used. Okay, this picture is there in NCERT book. This is source of alpha particle. So from this source, alpha particles are emitted in all possible directions. A fine beam of alpha particles is obtained using these lead bricks. Alpha particles cannot pass through thick metal sheets, so in this case lead bricks are used. This fine beam of alpha particles is made to fall on this gold foil, and this gold foil is supported by two pegs. So here is a gold foil like this. When alpha particles fall on the gold foil, most of the alpha particles will pass through the gold foil. Suppose if an alpha particle is scattered in this direction, and at that moment if microscope with zinc sulfide screen is present, then alpha particles interact with zinc sulfide screen, produces scintillation, means sparks. Those scintillations are observed using this detector, microscope. Okay, now if this is the direction of alpha particle, then this angle is the angle of scattering, theta. So this is angle of scattering measured with respect to direction of incidence. Initially alpha particles were traveling like this, so it is through which this angle alpha particles are scattered. Suppose this is the detector. To find alpha particles at different scattering angles, one has to take this detector at that angle. Now number of scintillations can be counted using microscope. To find alpha particles at some other angle, this detector should be moved. So detector is moved along the circumference of this arc, means circumference of this circle means all the points on this detector are equidistant from this point where alpha particles are incident. So variation of intensity with respect to distance can be neglected, because intensity of alpha particles is directly proportional to 1 by r square. If distance increases, intensity decreases. If distance is constant, intensity is also constant. So to keep the intensity constant, detector should be moved along the circumference of the circle like this. Okay, I hope you understood. We can also expect few alpha particles on the same side as the incident alpha particles. So if the detector is placed somewhere here, then the detector records scintillations, means alpha particles are found. So at every angle, number of scintillations are counted. That in turn represents number of alpha particles. Now experimental observations. Most of the alpha particles were found to pass through the gold foil without any appreciable deflection. So most of the alpha particles travel straight. Detector is here, means it records maximum number. As the detector is moved, that number decreases. And by this, we can conclude that atoms have lot of empty space. Because of lot of empty space, most of the alpha particles are traveling straight. Now, second observation. In passing through the gold foil, different alpha particles underwent different amounts of deflections. The number of scattered particles decreased with the increase in angle. Detector is here, it records maximum number. It detects maximum number means at theta equal to 0 degree. Theta equal to 0 degree. There could be as high as 10 power 7 alpha particles. Now, detector position is changed. So, at an angle 10 degree. 10 degree means like this. At an angle 10 degree, number of particles are counted. At an angle 20 degree, again number of particles are counted. So, at 20 degree, that's about 10 to the power of 5. So, at regular intervals, number of alpha particles are counted. So, let us plot a graph of number of alpha particles, scattered alpha particles versus angle as a function of angle. Now, even when the detector is close to the direction of incidence, somewhere here, then also the detector could record few alpha particles, meaning alpha particles after traveling straight are reflected or scattered. Now, third observation, a very small number of alpha particles practically retraced their paths or suffered deflection of nearly 180 degree. It is going straight and traveling back almost 180 degree means there should be some heavy positively charged particle. That heavy positively charged particle is reflecting this alpha particle because alpha is positively charged. If this positively charged particle approaches this heavy positively charged particle in the gold foil, due to repulsion, it can retrace. And later they said that this heavy positively charged particle is nucleus. Now let us see graph of number of scattered particles versus scattering angle. So at 0 degree, maximum number of particles. At 20 degree, the particle scattered alpha particles is less. With the increase in angle, the scattered alpha particles decreases. So at 180 degree, there is a small number. This number is very small compared to 10 power 7. Observe, this number corresponds to somewhere between 10 and 10 power 2. If this is 10 power 3, 10 power 2, this is 10 power 1, 10 to 100, small number, whereas this is 10 million. This is million, this is 10 million. 10 million is crore. So compared to crore, this number is very small. So this graph can be asked for 1 mark. Don't worry about the numbers. At least you should be able to draw this nature. And you have to mention what is there along y-axis and x-axis. There is a term defined in this scattering experiment called impact parameter, denoted by B. If this is a nucleus, reference line, median, and this is an alpha particle, velocity vector. As the alpha particle approaches this nucleus, which is positively charged, there is repulsion because alpha particle is also positively charged and this is also positively charged. Because of that, this alpha particle is deflected like this. Direction of incidence. This shortest distance is called impact parameter, denoted by B. Now, what is impact parameter means? It is the perpendicular distance of initial velocity vector of the alpha particle from the center of the nucleus. This perpendicular distance is called the impact parameter. I hope you understood. Suppose if impact parameter is minimum or 0. Impact parameter is minimum or 0 means if this is the direction of alpha particle, this is the nucleus. Students, can you guess what happens to the alpha particle? This alpha, as it approaches the nucleus, is retarded and it travels back. It travels back means something like U-turn. If it is U-turn like, then scattering angle is very close to pi, nothing but 180 degree. So if impact parameter is 0, implies that scattering angle is pi. Second case, small impact parameter means large scattering. This is the direction of alpha particle. This is the nucleus. Look at the direction of incidence. The direction of initial velocity vector is very close to the direction of nucleus. As a result, scattering is more. So we can call this as large angle scattering. So small impact parameter means small impact parameter implies that large angle scattering. Similarly, large impact parameter. Large impact parameter means this is direction of velocity vector, velocity. This is the nucleus, median. This distance is more. This distance is more means as the alpha particle approaches the nucleus, because of large distance, repulsion is less. So scattering is also less. Draw tangent. Using the tangent, one can find the angle of scattering. See, angle of scattering is minimum. So large impact parameter implies that small angle of scattering. Implies that if impact parameter is infinity, means if particle is very far from the nucleus, then scattering angle is 0, because practically there is no interaction between alpha particle and the nucleus. Now the distance of closest approach. This is the nucleus, positively charged. This is alpha particle. This is also positively charged, isn't it? Alpha particle means helium nucleus. Helium nucleus. Helium has 2 protons, 2 neutrons and 2 electrons. If you remove 2 electrons, then the remaining is helium nucleus. This helium nucleus is called alpha particle. So protons are positively charged, neutrons are neutral, therefore alpha is also positively charged. Now observe this case. Alpha particles or alpha particle is approaching the nucleus means the force of repulsion increases. Very close to the nucleus, the force of repulsion will be so high that alpha particle will retrace or get scattered. And this distance is called the distance of closest approach. See, this is alpha, positively charged. This is nucleus, positively charged. There are 2 charges separated by some distance means there is potential energy. And this potential energy of 2 charges should be equal to initial kinetic energy of alpha particle. So this is from the law of conservation of energy. Kinetic energy is known, then we can find out the distance of closest approach. And potential energy is 1 by 4 pi epsilon naught into charge of the alpha particle, 2 times E. Charge of the nucleus, Z times number of protons times magnitude of charge of the proton, divided by distance of closest approach. Let us denote it by R naught. R naught. So this is potential energy. This you have seen in second chapter, right? There are 2 charges, Q and Q means separated by small distance R. Then potential energy is given by 1 by 4 pi epsilon naught Q by R. Here first charge is charge of the alpha, second charge is charge of the nucleus. In this case, nucleus of gold. R naught. Kinetic energy, let me denote kinetic energy by just E. Okay. Then R naught, distance of closest approach, is equal to 1 by 4 pi epsilon naught into Z into E square, 2 times Z E square by R naught to the left hand side, E to the right hand side. So this is E. So this expression is required for 1 mark. Okay. Now outcome of the experiment. It is Rutherford's atomic model. The atomic model said, first point, an atom may be regarded as a sphere of radius about 10 power minus 10 meter. But whole of the positive charge and almost entire mass of the atom is concentrated in a small central core called the nucleus. Size of the nucleus is about 10 power minus 15 meter to 10 power minus 14 meter. There should be heavy nucleus, heavy particle which is positively charged. As a result of this, large angle scattering is observed. So keeping this large angle scattering in mind, the atomic model said there is a positively charged nucleus. Why it should be very heavy? Because upon impact of large number of alpha particles, the gold foil is not disturbed. The gold foil is not disturbed means they should be very heavy. That is first point. Next, nucleus is surrounded by electrons, leaving plenty of space in the atom. If this is positively charged nucleus and this is the electron, there should be plenty of space between positively charged nucleus and negatively charged electron. Actually, when we draw this type of diagram, according to scale, this is wrong, because size of the nucleus is about 10 power minus 15 meter and the size of the atom is about 10 power minus 10 meter. Students, give attention. 10 power 15 minus 15, 10 power minus 10. This distance is about 10 power 5 times. Means radius of the atom should be 10 power 5 times radius of the nucleus. It's a funny thing. Listen. If I draw nucleus of radius 1 centimeter, this is schematic representation. If this is a circle of radius 1 centimeter which represents nucleus, then first electron should be at a distance of 10 power 5 times. What is 10 power 5 times centimeter? Centi is 10 power 2. It is 10 power 3 meter. 10 power 3 meter is 1 kilometer. Means if I represent this by if I use this to represent a nucleus, then first electron should be drawn at a distance of 1 kilometer. Just imagine, I should take my vehicle and travel through a distance of 1 kilometer, and from there I have to show first electron. So what is there between the electron and the nucleus? Means nothing. That nothing is empty space. Next point. Since atom is electrically neutral, the total positive charge of the nucleus is equal to total negative charge of the electrons. Atom is electrically neutral. This is observed. So atomic model should conclude that total charge of the nucleus should be equal to total charge of electrons. If there are number of electrons, then net negative charge should be equal to net positive charge. Thereby, atom is electrically neutral. Electrons are not stationary, but they revolve around the nucleus. The necessary centripetal force is due to electrostatic force of attraction between electrons and the nucleus, and the orbits are circular. This is simplest approach, circular orbit. The atomic model did not consider stationary electrons. If electrons are stationary and nothing is there between electrons and the nucleus, then these electrons will fall into the nucleus, isn't it? Thereby atoms will collapse. To explain this, atomic model assumed that electrons should be revolving around the nucleus. For the motion of electrons, there should be centripetal force, and the necessary centripetal force is provided by Coulomb's force of attraction between electrons and the nucleus. These are charged particles, therefore there should be attraction. Coulomb's force. Students, again go through the points. Now let us go to merits of Rutherford's atomic model. Merits of Rutherford's atomic model. The atomic model explained electrical neutrality. Yes, true. Because net positive charge equal to net negative charge means total charge equal to 0. Second point. The atomic model incorporated the concept of orbits and motion of electrons around the nucleus. So just like solar system, this atomic model for the first time incorporated orbits. Orbits means motion of electrons. So it used motion of electrons concept and orbits concept. So what are the demerits means? Of course, the atomic model is not complete since it is based on assumptions. There must be demerits. So what are the demerits means? First demerit, the atomic model could not explain origin of line spectrum. Spectrum. Again, in the next topic, let us see what is spectrum. For time being, if this is a glass chamber filled with hydrogen gas at low pressure, and they are provided with two electrodes, one of them connected to positive, other one connected to negative. Because of suitable potential difference, the gas, hydrogen gas at low pressure, starts emitting radiation. So this is radiation due to hydrogen. Okay. So what is the origin of radiation, emission of radiation by hydrogen atom means? There is no explanation by this atomic model. So that is one limitation. Students, you are going to study more about the spectrum in the next topic. Second limitation or demerit. It was very disappointing. The atomic model could not explain stability of atoms. Stability. Why it could not explain stability means, if this is the nucleus and here is an electron revolving, then there is attraction between negatively charged electron and positively charged nucleus. Because of that attraction, this electron is constantly pulled towards the nucleus. As a result, it approaches the nucleus. As it approaches, the electron should lose energy. So the loss of energy is in the form of radiation. When it loses energy, then attraction is stronger. If attraction is stronger means electron further approaches the nucleus. There is again emission of radiation. Electron approaches, finally takes the spiral path and falls into the nucleus. According to the atomic model, it should fall into the nucleus with the emission of continuous spectrum. If atom is there and electron falls into the nucleus means atom collapses. Atom collapses means there are no more atoms. There are no more atoms means that cannot explain stability. Because whatever atoms we see here, they are all stable atoms. There is no point that these atoms will collapse, should collapse. But the atomic model is telling that atoms will collapse. Atoms are not collapsing, therefore the atomic model is not complete. That is a demerit of Rutherford's atomic model. Now go through once.